Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics. And today we're looking at acceleration due to free fall. And I want you to recall the value of gravity on Earth, calculate the velocity when an object falls due to free fall, and describe the link between gravity and weight. Okay, so there are three LOs. So, little starter question. I'll use this formula. Acceleration equals displacement divided by half times the time squared. Now, just to be clear, you do not need to memorize this formula. It's not one you need to know for IGCSE. However, I have seen questions where they will give you the formula and ask you to use it. So that's why I'm including it. And it's also useful for calculating gravity, which is the kind of question where you will see it. So a runner starts from rest and reaches his maximum velocity after 3 seconds. In this time, he travels 27 meters. Calculate his acceleration. So acceleration equals displacement divided by a half times time squared. Sometimes you might actually see it's written as 2 times displacement divided by time squared, the same formula. So 27 divided by a half times 3 squared. So 3 squared is 9, half that's 4.5. So 27 over 4.5, which equals 6 meters per second squared. Don't forget your units at the end of the answer. So the reason I put it on the start is because we are going to use it as well today. So this is, if I was teaching this in the class, then I would get my students to do a short practical. So what I normally do is get them to drop a ball from a height of 1.5 meters. So we use a tape measure or 2 meter rulers, mark out 1.5 meters, drop it, start the timer when, so you do it in pairs. Let's go of the ball and start it. Sorry, started when they let go of the ball, stop it when it hits the floor. And then you can calculate acceleration using the formula acceleration equals displacement divided by a half times time squared. Now, the only issue with this is there's quite a lot of error. So human reaction time is about quarter of a second. So if you're looking at a quarter of a second when you start and quarter of a second at the end, that's half a second. If if it takes, say, 1 second to fall 1.5 meters, then that means you're looking at about 50% error, a huge amount of error. Now, that will increase the time likely to stopping the reaction time. So if you increase the time, that means you should get an undervalue of acceleration, or sometimes it can work the other way, because you might preempt the person dropping the ball, but generally you'll get a lower value of acceleration than you would expect. So this isn't a great method to calculate gravitational acceleration. Now, this is a much better method using something like this. So it's a piece of equipment where the electromagnet and it's attached to a timer where on-off button for the timer also turns off the electromagnet. The ball bearing is obviously made of metal, it's attached to this, or it's magnetized to it rather. I press the button, starts the stopwatch, and when this trapdoor here feels a large force, i.e. the ball bearing falling on it, then it stops the stopwatch and we get a really, really good indication of the time. And even when you do this, it gives you to sort of well, it's got a resolution of about 0.001 seconds or 1 millisecond. So when I've done this practical with students, normally all the answers are within 1 millisecond of each other, unlike the first method where there's a lot of variation. And when you do it this way, you tend to get a value very, very close to the true value of gravitational acceleration, which on Earth is 9.8 meters per second squared. Sometimes you'll see it, some questions, occasionally you might say approximate it as 10 because it makes life and calculations easier. When you get to A level, you use 9.81, but at IGCSE, we generally use 9.8 meters per second squared. So what happens if I throw a ball upwards? Well, then it's decelerating because it's always accelerating towards Earth. So if you're throwing it upwards, the velocity is up, the acceleration is down. So we'd say it's decelerating upwards due to gravity on Earth, but it's still the same value, 9.8 meters per second squared. So an object is dropped off a bridge with zero initial velocity. Calculated velocity after 5 seconds, assuming air resistance is negligible. So the initial velocity is zero. Final velocity is what we're trying to work out. A is 9.8 and T is 5. V equals U plus AT. So 0, because it's starting at 0, plus 9.8 times 5, which is 49 meters per second. Try this one yourself. Pause it, and then I'll put the answer on now. You get a final answer here of 104 meters per second. Okay. Here are 3 questions for you to have a go at. When an object is dropped, it accelerates due to gravity. When it is thrown upwards, it decelerates due to gravity. On the moon, gravity has a value of 1.6 meters per second squared. Assuming air resistance is negligible, will an object fall faster on the moon or on Earth? Well, a quick reference to that, air resistance is 0 on the moon, but it does happen, you do get air resistance on Earth. However, in this question, we're saying ignore air resistance. So it's going to fall faster on Earth because the value of gravity or gravitational acceleration is about 6 times higher on Earth. Bob drops a ball down a hole. V equals U plus AT to calculate the velocity after 5 seconds. If he just drops the ball with 0 initial velocity, so put our numbers in, 49 meters per second, which is the same as what we did earlier. However, if he throws the ball with initial velocity of 10 meters per second, it's going to be the same answer, but with 10 meters per second higher. So it's going to be 59 meters per second. We'll use the formula just to prove that it's 59 meters per second. Slightly harder question. Mr. Dave throws the ball up with an initial velocity of 25 meters per second. Calculate how long it will take to reach its maximum height. Okay, so its maximum height, at its maximum height, sorry, its velocity will be 0 because I'm throwing it with initial high velocity, it's decelerating, and once it reaches 0 meters per second, it starts to fall back down. So its maximum height is when V is 0 meters per second. So U is 25 meters per second, V is 0, A, I'm throwing it up, so it's going to be negative 9.8. And T, so we're trying to work out. V is U plus AT, T is V minus U over A. Remember, V is the final velocity and U is the initial velocity. Still out there. 0 minus 25 divided by minus 9.8 gives you 2.55 seconds. Now, I could actually extend this question by saying, so how long will it take to actually reach his hand? So throw it up and then come back down and hit my hand. And all we do is double it because the time it takes to go up is the exact same as the time it takes to come down, assuming no air resistance. So in that case, it will be about 5.1 seconds. So we know acceleration due to gravity on Earth is 9.8 meters per second squared. And I'm going to look at the link between gravity and weight now. So we know F equals ma. W is mg, so weight is mass times gravity or gravitational field strength. So G, you can see it's W over m, newtons per kilogram. But we also know it's acceleration. So gravitational field strength is measured either meters per second squared, because it's acceleration, or newtons per kilogram. Both are acceptable. So here's a past paper question. Gravitational field strength was 8.8 newtons per kilogram on Venus and 3.8 newtons per kilogram on Mars. An object has a weight of 42 newtons on Venus. What is the mass and the weight of the object on Mars? So the mass is the same on every planet. Mass doesn't change, weight does. So we can work out, the mass by looking at our values on Venus. So W is mg, m is W over g. So weight, 42. Gravity, 8.8. Figure 4.77 kilograms. So we know now it's either A or B. So to two sig figs, it's 4.8. So weight on Mars equals mg. Mass is 4.77. G on Mars is 3.8. Multiply them together, you get 18.1. So the answer is A. And finally, a coconut falls from a palm tree. At X, it is just starting to fall. Y is the point just before it hits the ground. What is the acceleration of the coconut at X? Air resistance can be ignored. Well, acceleration is always the same when this object is falling. It doesn't change if there's no air resistance. So it's going to be the same. So the answer is therefore C. Okay, thank you very much, everyone. I'll soon be uploading the next lesson, which will be on terminal velocity. I'll see you there. I'll link it as well down below. Thank you and bye.